Hello, this is part 2 of Cascade Control. Basically, we're going to be doing the same as we did in part 1, but we're going to change things slightly. In part 1, we placed all four poles and all four gains at the same time. All four poles were placed at the same location, and it was very simple to do. But the problem with that is if you ever have to drop out of position control and use velocity control only, the poles may not be where you want them to be, so you might not always get the desired results. Now, as it turns out, in part 1, we were lucky or fortunate, and the poles happened to be in pretty good locations. But to make sure that the inner loop poles are in good locations, what you need to do is place those first, and that's what we're going to do here. So I'm going to start with the same open loop plant as before, and the same PI control. We're going to have the same transfer function, the closed loop transfer function, and make substitutions. And again, we're going to have only the integrator gain act on the error. The proportional gain is going to act on changes in the position, or actually changes in velocity. And then this is the simplified transfer function with the characteristic equation in the denominator. And this is the desired characteristic equation. What we're going to do is we can place this anywhere we want. So this is the difference between what we're doing in part 2 here versus part 1, is we're placing the inner loop poles first at any desired location. And I'm going to put them on the negative real axis so we get a critically damped response. So moving up, I'm going to solve for the proportional and integrator gains symbolically. I have a shortcut way of doing it so that I have the symbolic formula for the integrator gain here and the symbolic formula for the proportional gain here. Now, given that we have the inner loop tuned up, so it basically acts like a two-pole real filter, we can use that as the plant for the outer loop PID. So this is the inner loop from above, and because it's a velocity transfer function, we have to integrate it. 1 over s integrates, and that makes it a position system. Same thing here, and again we have the PI controller with the integrator acting on the errors between the target and actual position in this case, and here the proportional term is only acting on changes in position. Now, as you can see, this is a 4-pole polynomial, and to solve for the gains we have to be able to equate 4 equations so we can solve for 4 unknowns. So what we use is the coefficients from the desired transfer function from well, this is the actual transfer function. This is the desired one here. And so we have these two sets of polynomials, or coefficients for polynomials. And I'm going to equate them just like I did in part 1. So this is the 0 power of s, first power of s, second power of s, and third power of s. And now I can solve for my 4 unknowns. And my 4 unknowns are the integrator gain, proportional gain, and then I have to have 2 pole locations. So unlike the first example, I can't place all 4 poles at the same point because I need to have 2. So I have 2 variables for the 4 equations and 4 unknowns. Now this solution is interesting. There's actually 2 sets of solutions. The one in the first column is not valid because here the integrator gain and the proportional gain are negative. Over here they're positive. And we can see how they simplify down to as functions of lambda. And what's interesting is that just like in the first example, the outer loop gains are only proportional to this lambda. And in this case, instead of just having all the poles being at minus lambda, we have just the inner loop poles at lambda. The outer loop poles are going to be at 0.211 times lambda, and this new is going to be 1.37 times lambda. But basically, the outer loop poles are not dependent upon the open loop parameters, for instance, the gain and the bandwidth, like the inner loop happens to be. So let's try this out. Because the outer loop poles are going to be slower or closer to the origin, here you can see that it's almost like a fifth of the of lambda. What I did is I made lambda a little bit bigger. These are the same parameters as before. And I calculate the inner loop, well, the inner loop gain formulas were already calculated up above, but now I'm adding values to this. So this is my outer loop integrator, my outer loop proportional gain. And then here are the pole locations in radians per second. This next part is the closed loop control. And like before, I have the changes in the state. This is the state space, just updating the state with the control output from the iteration before. The first thing we need to do is calculate the target velocity for the inner loop, and that is dependent upon errors in position here and changes in position here. The outer loop is limited by the plant gain. For instance, the K is 10 millimeters per second per percent, and that's percent control output. So if I multiply that by 100%, I get a plus or minus 1,000 millimeters per second is my limit. The inner loop is calculated immediately after. This makes life very simple. The inner loop, since it's a velocity loop, is going to act on, or the integrator gain is going to act on the error between the outer loop velocity as calculated, or actually it's the inner loop target velocity, and the actual velocity. And then again, the proportional gain is acting only in changes in the actual position or actual velocity. And since this is going directly to the drive or the actuator, it's limited to plus or minus 1%. Then you can scale that down to plus or minus some current, or plus or minus 10 volts. So as above, we're going to first make step jumps. And like I said before, I like to test step jumps because that lets me know how robust the system is as far as whether or not it's going to overshoot or the integrator is going to wind up and cause problems. And you can see here that the outer loop control is actually fairly good. We have the actual position. It's going to the step here. You can see the outer loop, or the output for the inner loop target position, saturates at 1,000 millimeters per second. Then it goes down to 0. There should be a 0 line right here. And I make another step jump. You can see that it approaches and it doesn't overshoot, even though the velocity is saturating. Then here's the inner loop. And you can see there's a little bit of phase delay. The control output is saturating here. And then the target and actual are following pretty closely while accelerating, but while decelerating, you can see the actual velocity is lagging the inner loop target velocity by just a little bit. But for the most part, the response is very good. There's no overshooting, no ringing, no problems with saturation. So let's see how it does with a sine wave. Again, this is using the same parameters as above, and you can see the output of the outer loop, and this is the target position and the actual position. And you can see that the output is leading the errors in position here. And that is good because the inner loop velocity needs to lead the position by 90 degrees. That's just the way it works with sine waves. So you can see that the inner loop target velocity and the actual velocity are right on top of each other, which means the tuning is very, very good. So now let's calculate bandwidths. Again, I'm kind of skeptical about a lot of the things I see on the internet. There's an awful lot of people that say, well, the outer loop's got to be, 10 to 15 times faster than the inner loop, and it's not necessarily so, and I'm going to show how you can compute this. This is the inner loop transfer function, and all I did is I replaced the S with j omega so I can calculate what the, this is a 3 dB drop here, so this kind of finds where the 3 dB point is. That's for the bandwidth. You can see the bandwidth is 161 radians per second, or about 25.7 hertz. Then I have the outer loop bandwidth, and basically I use the inner loop here for the inner position plant. And then I have the outer PI control here. And again, I do the substitutions for S, and I get a, well, by the time I get done, it's 4.288 hertz for the bandwidth, and so the ratio is about 6 to 1. So let's look at the Bodhi plot calculations. These are the same calculations as before, and you can see that because we have the two poles placed on the negative real axis, we're going to get a response that looks like like a two-pole low-pass filter, real low-pass filter. You can see that with two poles, you're going to have 90 degrees per phase leg per pole at the higher frequencies. And the outer loop Bodhi plot is similar. And again, it's because all the poles are on the negative real axis, although they're not all in the same spot. The three poles that are closest to the origin, the mu poles, are going to be dominant, and so this is going to basically look like a three-pole low-pass filter, because the nu pole is so far off to the left it's going to decay or cause the errors to decay fairly quickly, or it's part of the errors to decay quickly. So I'm going to plot the poles and zeros, and you see the inner loop poles are placed at minus 251. Now, due to all the round-off errors in the calculations, it says there's a small imaginary term, but the real value should be lambda, which is 251 radians. And then the other two outer loop pole locations should be 53 and 343. So you can see that this is where the outer loop poles happen to be, and if we did put the integrator or the proportional term in the forward path, there would be a zero at this location, and that might cause some problem, because if you scan from the origin to the left, the gain would start to increase, and it might go above unity or 0 dB, and then it would only attenuate once it gets past or close to the outer loop pole locations. So this is fairly simple. I think the key thing here is to realize that the outer loop gains and pole locations do not depend on the inner loop parameters, except for the lambda. That concludes this video.